For having me here at the OC3. My name is Harald Hoyer. I work for MetaLabs as the lead trusted execution engineer. We MetaLabs are passionate about liberty, blockchain and math. We are known as the creator of zkSync Era. So if you want to know more about zkSync, head over to zkSync.io. For zkSync Era, we are a blockchain operator. And this is why this project I want to present here came to life. The goal of the project is to secure our secret keys. As a blockchain operator, we have several of them. For example, to access Layer 1 contracts, fee wallets and cold wallets. Those in possession of the secret keys today currently have to protect a lot of money. This project should take the burden off their shoulders and set the bar higher for any attackers. Our main requirements for this project are a key value store, holding our secrets running in a TE. And no single person should have access to a single secret. Every step in the setup, administration and whatever has to be signed by M out of N people. Every secret has to be created in a TE and should never leave the TE space. This means things like blockchain transaction signing should happen in the TE. The key value store should of course have high availability. Multiple TE technologies have to be used, because in case one of them has serious problems, we would just shut down these instances. With these requirements we went shopping, but no solution on the market fulfilled our requirements, especially the M of N signatures for the administration tasks. So we decided to develop our own solution. Of course, we could have implemented our own key value store, but also maintaining that with high availability was not in scope. Hashicorp Vault is such a key value store which you want to run in a TE. It is state-of-the-art, open source and was even free open source until last year. Vault is more than a key value store, so in the end we would open much more features than just storing secrets. It supports authentication plugins and with the Raft store some level of high availability. For the SGX runtime environment, our choice is Gramine. It is actively developed and lift and shift is easy for normal applications. First evaluations showed that Vault can be run on Gramine, which in the end worked out. After some bugs have been fixed last year in Gramine, Vault works fine with the Raft storage. Here is a brief overview of the end setup. We have the unseal TE, which unseals Vault, catches the root token and configures Vault with the attestation parameters of the admin TE. The admin TE authenticates to Vault via remote attestation and executes administration tasks for Vault. A normal application TE also authenticates via remote attestation and can then operate Vault with the received token just as normal. So the first step to our end goal was the development of an authentication plugin for TEs for Vault. This lets TEs get a token after successful remote authentication. You basically replace the password with either the hash of the TE or the hash of the public key signing the hash of the TE, which is MR Enclave and MR Signer in SGX. We started to implement SGX first because at the time of the project start, neither SAV, SMP nor TDX was available in public clouds. The Vault plugin wants the TE to send the attestation quote and the collateral data in the authentication step. In return, the TE can do remote attestation TLS or manually challenge the plugin and get its attestation quote. In the end, the TE receives a token from Vault, with which it can go shopping in the Vault instance. Of course, only as much as the token policies allow. The plugin is available in our GitHub space under the Mozilla public license. This plugin runs with Vault in a container and in the Gramine runtime. Of course, the container has to be built reproducibly. Doing this with traditional distro packages means that you can't modify any of them, except if they can be built reproducible, which means that you have to lock and cache the build environment and all of the build dependencies. This all goes out of hand quickly, except if you use something like Nix, which is kind of designed to do especially this. For our needs, we created the small Nix SGX repo, which holds all updated or modified components needed to build our containers. Even on non-Nix OS machines, it is easy to reproduce the builds and therefore the TE hashes, which in SGX corresponds to the EMMA enclave values. The last repository in the mix is Tpot. Here we collect the TEs needed to initialize and administer the Vault instances. It also holds client tools to talk to those TEs from the outside non-TE world. Additionally, we added some pre-exec helper tools. One of it is used to create signed certificates for Vault to enable remote attestation TLS. Others load some secrets from the Vault instance and provide them to the main process as environment variables. This eases the lift and shift process a lot. So one of the Tpot TEs is Vault itself with the authentication plugin, the Vault configuration and the pre-exec tool to create the Vault TLS certificate. The pre-exec is necessary because Vault relies on a certificate chain for TLS, and for our setup, remote attestation TLS is only needed. Therefore, we have to have a kind of public CA where we have the private key in the TE to create a signed certificate with the remote attestation extensions, including the attestation quote. This CA can be public because we don't rely on our TLS certificate chain, but we rely only on remote attestation TLS. The first needed TE for bootstrapping is the unsealed TE. It is basically a proxy between you and the Vault instance. For unsealing, you have to tell Vault your public GBG keys of the super administrators to receive a secret for unsealing. This is built in Vault and already follows an M of N scheme. In this step, the unsealed TE also wants your admin GBG keys for the M of N signature scheme, which we will see later for the admin TE. The unsealed TE initializes Vault and returns the GBG encrypted secrets for all N superadmins. Now M of N superadmins send the unsealed secret to the unsealed TE, which proxies that to the Vault instance. Finally, Vault is unsealed and the unsealed TE catches the root token from Vault without reporting it to the outside world. With the root token, the unsealed TE installs the authentication plugin, configures the admin TE authentication parameters, adds the admin policies and stores the N admin GBG keys and additional admin configuration. As the last step, the root token is revoked. Of course, a new can be generated as a last resort with the normal Vault unsealing process. There is no TE needed for that, we just talk to Vault. So in case everything TE related fails with the super admin GBG keys, you can always recover anything in the Vault instances. The admin TE logs into Vault via the authentication plugin and executes recipes after checking that it also received signatures from N out of N admins. One of the recipe types is signing, where the admin TE will create a signing key for a TE name and sign an SGX6 struct file with this key. Another recipe type will execute a batch of raw HTTP puts to the Vault instance for any kind of Vault operation. Part of the recipes is also the last digest parameter, which is the hash of the last executed recipe. With this, everyone signing a recipe also signs the past history of admin actions, and therefore an admin can recognize that something is missing in the known history. For any application TE which needs to access the Vault, the authentication parameters will have to be written via the admin TE, along with the ACL policies, so that in the end the application TE can authenticate via remote attestation and has access to everything the admins granted. Here you can see a raw signing request, which has to be signed by M out of N administrators. The raw data included is the SGX6 struct, which includes the hash and signature for the TE, along with all other SGX relevant settings of the enclave. This request can be reproducibly generated by every admin from the original 6 struct of the enclave container, which the admin of course reproduced himself, also with the help of the Nix build process. So the admin signing this can be sure he only signs what he meant to sign. Another admin recipe example here is the installation of a new TE, along with its authentication parameters and vault policies. It only grants access to a certain secret path after the TE authenticates to Vault with the specified remote attestation parameters. Here the TE is authenticated via the named TE example and its SGX MR signer hash. To bootstrap the whole setup to a point where every component is signed with a key generated in TE space is a little bit complicated, but these steps have to be done only once at the very beginning. The Vault Raft cluster helps here to replace every Vault instance one by one. Having everything pinned to a signature-based setup helps to roll out updates without changing other components in the process, which you would have to do if you only relied on the MR signer. Of course, the whole thing is not yet complete and has a lot to be implemented still, like rotating the super admin GBG sealing keys, removing and adding the normal admin keys, adding other TE technologies, and much more. If you want to help, just contribute to the repositories mentioned here, or fork them and run your own modifications. It's all open source and has permissive licenses, mostly Apache and MIT. Lastly, I want to mention some of the obstacles encountered while developing the whole thing. The Azure DCAP library, for example, seems to return outdated collateral, which leads to unsuccessful remote attestation. There's a simple patch for that, but the PR for it sits there unanswered for months now. It could also be fixed by Microsoft updating their DCAP infrastructure. Also, Azure SGX instances have a fairly old kernel which does not support EDMM, but this will change over time, hopefully. For Vault, the plugin loading sometimes takes so long that the Raft algorithm decides to drop leadership to the next instance, which then starts to load the plugin also and loses leadership while doing so. This can be prevented by playing with some timeout parameters to the Raft algorithm, but these slow down the first initialization significantly. Another thing is the base Intel SGX libraries do not compile reproducibly, because Intel decided to add some C++ microservice stuff which adds zip files to the binaries, which also include creation timestamps. In the Intel SGX data center attestation primitives, Intel added 2 Rust crates for attestation last year, but they contain some unsound FFI code. Also, the install and packaging process is a mess. In addition, the whole project does not even support parallel make. Alright, enough ranting. Thank you for listening. I hope you find this project interesting and want to use it and maybe even contribute to it. We will now enter the Q&A session where I will answer your questions. Thank you for listening.